So I'm glad to start the next year of the seminar. I have been lazy. I'm not sure when the next talk will be. No earlier than in 2 weeks, but maybe actually in a month or something. So just because now there are many live seminars, so both me and as we can see, many from the audience prefer it live. Let's hope that we will be able to continue live like this. Continuous frontal talks. Okay, so the YouTube seems to work. Okay, very good. So I am glad to present Subhajit Jana from Queen Mary University of London and announce his talks on local L2 bound on Eisenstein series and applications.
Okay.
Yes.
Sorry. Thank you very much, Dima, and thanks, Erez, as well for inviting me to give a talk. Very happy to give a talk at WIS. So today I'm going to speak about our recent work on a local L2 bound on Eisenstein series and its applications. This is a joint work with Amitay Kamber. Probably many of you guys know Amitay. He was a PhD student of Alex Luborsky in Fuji. So the talk has two parts. The first part is about the applications, and the second part is about local L2 bound of Eisenstein series. So I'll go in the reverse direction of the title. Okay, so let me go with the application first. So I want to talk about two arithmetic problems. So the first one is about Diophantine exponent. So let's say P is a prime number. We know that Z1 over P. We know that Z1 over P is dense in R. Our goal is to make this density of Z1 over P in R quantitative in some fashion. And similarly, we can ask in a general picture that using the fact that SLN Z1 over P is dense in SLN R, we want to make this density quantitative. So how do we make a density quantitative? We have in mind the Dirichlet type approximation. So if we want to make a given number in SLN R approximated with a given approximation error, say epsilon, how complex the rational points in SLN Z1 over P has to be. So that's the basic qualitative question. So let me define first some parameters or measurements of complexities and approximations. So one of the usual definition of complexity in rational matrices is by its denominator. So how do we define denominator? We define a height function on SLN Z1 over P is valued on non-negative integers. We say that an element in SLN Z1 over P has height k. The height is defined by the minimum of all cases that P to the power k gamma is an integer matrix. So it's basically the LCM of all the denominators in the entries of gamma, and we take log p, log base p of that. So that's the usual definition of denominator. Then if you want to approximate in manifold, then we need to have some sort of measurement of distance. So because it's a Lie group, it's better to talk about a Riemannian metric. In fact, SLNR Riemannian metric, let D be such a metric. And let's say X and X naught are 2 points in SLNR mod SONR. So I could have talked about SLNR itself, but just for simplicity of this talk, I'm dividing by the maximal compact subgroup of SLNR and talking only on the symmetric space of the group. So this is the definition of a Diophantine exponent. Okay, so what is the definition? So we call kappa x comma x naught to be the Diophantine exponent of x comma x naught, which is the infimum of all zeta, so that the following system of equation has a solution. So what is the equation, or what are the set of equations? The first one is the distance between gamma inverse x comma x naught is bounded by epsilon, meaning that x naught and x can be, if you think x naught to be the identity coset, then gamma approximates x by approximation error epsilon. And gamma has complexity given by some number zeta times epsilon, the logarithmic of epsilon inverse. Okay, this is some sort of very natural question. We are interested in approximation with approximating error epsilon, but we want to understand how large the denominator of the rational matrix would be. And we want to define the Diophantine exponent to be the minimal of such zeta, or the exponent of p, so that this approximation has a solution in gamma in SLN Z1 or p. Okay. And then for fun, we also define another quantity called kappa is just infimum of all tau, so that this Diophantine exponent is smaller than tau for almost every x comma x naught. Almost every in the sense coming from the Haar measure on SLNR. All right, so this is called Diophantine exponent. Let's see what we can talk about this gamma. I'm sorry, the kappa, the Diophantine exponent. So this is a very cute argument about using the covering. So we want to approximate the whole or almost every point in the symmetric space by epsilon error. So what we do, we consider an epsilon ball around this point x naught. We hit the ball by all the gammas with height, let's say, bounded by k. Then this shifted ball should cover the whole space, or almost cover the whole space. By almost, I mean it probably may leave a measure zero set. So to do that, if we do the calculation very rigorously, we would need that this kappa at least has to be the ratio of these two volume in some sense. So the volume of the numerator, the numerator is a volume of the epsilon ball, and the denominator is some sort of volume of a periodic ball, but which is we can think as the number of cosets whose height is bound by k. And if we consider this limiting procedure, and we would end up this quantity half times 1 plus 1 over n. And this covering argument says that to approximate things with epsilon error, we must need this kappa to be at least of this size. So the question is, so this is a necessary condition. The question is this a sufficient condition as well? So can we also approximate almost every point with this Diophantine exponent given by half 1 plus 1 over n? So this is the conjecture by Ghosh, Gornick, and Nevo. So Ghosh is Anis Ghosh, Alex Gornick, and Amos Nevo. So this conjecture is posed in different papers by them, starting from 2014 to 2018. I'm just picking up one of them where the conjecture is the most generalized in some sense. The conjecture says, the thing I just said is that this number indeed is optimal, in the sense that almost every point can be approximated with the given exponent given by this quantity. All right, and they also pose similar conjectures for large class of algebraic varieties, but we're only focusing on the symmetric space case here. Okay, so let's see what are the results on this towards this conjecture. So Ghosh, Gornick, Nevo in 2018 proved that this kappa is optimal for SL2, but on the assumption of the generalized Ramanujan conjecture for mass cast forms on SL2. And unconditionally, they can only prove that kappa is bounded by 24 over 25, which is strictly smaller than, if you plug in 2 here, which is 3/4, strictly smaller than, I'm sorry, strictly bigger than 3/4, this quantity. So this is not optimal without Ramanujan conjecture. And again, without any hypothesis, they proved that this kappa, or they could prove that this kappa is only smaller than this quantity, where the thing in black is what we conjecture to be optimal, and they can only prove a certain factor of that, certain factor is bigger than 1. All right, any question so far about this conjecture? And okay, so let me go to the second problem, because I promised to talk about 2 arithmetic problems, and this second problem is very similar. This is called optimal lifting problem. But in some sense, this is a dual of this optimal Diophantine exponent problem. Why it is a dual, I will tell maybe in 15 minutes or so. So the lifting problem is the following. So let Q be a positive integer. Consider the projection map SLNZ to SLNZ mod QZ, the mod usual mod Q map. This is elementary to prove that this map is surjective. In fact, follows from the Chinese remainder theorem. Let us fix a norm on SLNR. Let's say the Frobenius norm, which is given by G maps to the trace of G transpose G and the square root of that. So let us ask this question. So pick a matrix here, gamma. We want to understand the pre-image of gamma, whose norm is bounded by T. So the question is the following: how small T can be, so that we can find for every gamma in SLNZ mod QZ has a pre-image gamma tilde, but norm is bounded by T. This is kind of similar sort of problem as the previous problem, but the role of Archimedean and non-Archimedean in some sense is reversed. Of course, we may understand that if T is too small, we may not have a lift even. That can be checked. There are matrices without lift if T is super small. So T needs to have a certain size. And this is very similar to the covering argument we gave last time for the last problem. This is something sort of pigeonhole principle. And similarly, it can be proved that one must need the size to be q to the power alpha, where alpha is this kind of ratio given by 1 plus 1 over n, to have lifts of norm bounded by q to the power alpha. And this is, you may notice that this 1 plus 1 over n also appears here with a constant half. Okay. Right. Okay, so there's a conjecture by Sarnak in one of his letters to, I think, Aronson and Pollington. Okay, sorry, there are two chat. Oh, sorry, is it good? Any question? I cannot see the chat box actually. So if there is a question, please just ask me. That's better. Okay, the conjecture is that almost every gamma can be optimally lifted. That means that if we choose the norm to be bounded by the norm of the lift bounded by 1 plus 1 by n plus epsilon, epsilon is something very small, there will be almost no gamma who doesn't have a lift, meaning there is the number of gammas or the proportion of gamma which doesn't have a lift of this size is of the order q to the power negative delta. So that means that almost every gamma can be optimally lifted. All right. And there are also similar question can be asked for other reductive groups, and this is an ongoing work by Shaivra and his collaborators. Okay, let me again talk about the progress towards this conjecture. So the first one is due to Peter Sarnak himself in 2015. This is that optimal lifting conjecture is true for SL2. Second one is very recent due to Edgar Assing and Valentin Blomer in 2022. They proved if Q is square free, the optimal lifting conjecture is true for SLN, but on the assumption on a sharp estimate of the local L2 bound of Eisenstein series. Okay, so this is a mouthful. So there are some Eisenstein. There's something something called Eisenstein series in the automorphic spectrum of GLN, and in some sense, we need some estimates on their how their local L2 norm grow as the parameters of the Eisenstein series go to infinity. So I'll talk about this later. In fact, this is the main thing about my second part of the talk. But just to give you the result, I just say that they prove the result on this on the assumption of this hypothesis. Okay, any question until now on these two problems? All right. So let me talk about our results. So these are the results I obtained with Amitay. The first one is about the optimal exponent. So we proved that for SL2 and SL3, kappa is optimal. That is removing the condition on assumption on the generalized Ramanujan conjecture from Ghosh-Gordnik-Nebel's paper for SL2, and for SL3 is anywhere we proved unconditionally. For SLN, we proved that this kappa is optimal, but on the assumption of something called Sarnak's density hypothesis. You can think this density hypothesis in some sense is a weaker version of the generalized Ramanujan conjecture. I will talk about this, the density hypothesis maybe after 2 or 3 slides. But on this assumption, which is something weaker version of the GRC, we have that kappa is optimal. And unconditionally, we have some upper bound of kappa, but this is very, very close to the optimal. So recall that this thing is this half times 1 plus 1 over n was the optimal one. We just have a little bit more than that because as n goes to infinity, this thing is essentially 1. And whereas Ghosh-Gordnik-Nebel had n minus 1. And the second theorem is for us is the optimal lifting conjecture is true, again, for Q square free for SLN. Okay, any question about the theorems or anything? All right, if not, let's look at the proofs of the proofs that we did for these two theorems. And both proofs more or less have the same scheme. So let me just give the schematics of the proof in a very abstract way. I recognize that this is a representation theory seminar, so I kind of assume lots of representation theoretic material without properly telling what they are. But if there is any question, please ask me. Okay, so what we do, we somehow embed this problem. So both of the problems are some sort of about the geometry and arithmetic of SLN Z mod, SLN Q inside SLN R. When we do, our goal is to understand this geometric problem in terms of some sort of automorphic problem, and the machinery that goes into the proof is some sort of trace formula. That's kind of the general big picture of our proofs. So what we do, we kind of embed the whole problem into a automorphic space. The automorphic space is PGLN of Adel mod PGLN of Q. So we kind of have in both of the proofs a compact subgroup, let me call it K, and some master parameter T that goes to infinity. So I'll give you a specific example after 3 slides where one of this K and T would be clear what they are. But let me first tell you the scheme. Then what we do, we choose a test function on PGLNA, a smooth, compactly supported K-finite function, which implicitly depends on T in some sense. Then what we do, we construct the automorphic kernel, which is defined by the sum over gamma in PGL and Q and the quantity f x inverse gamma y. This is called automorphic kernel. What is our goal? Our goal, the geometric problem can be reformulated in the following sense. So we fix a compact set omega inside the fundamental domain. Then both of the problems, in some sense, can be reformulated in the following questions. We need to prove that Kf is not too small all the time, in a sense that if we consider Kfx and assume considering it's a function of the second variable, we prove that its difference with some size 1 main term and the L2 norm of that, and then we average over x. This thing is not too big. Like this thing is grows at most t to the power epsilon. So t is this master parameter. So this is essentially bounded. And how do we treat this problem? We apply the spectral decomposition of the space PGL and A mod PGL and Q mod K. Then the above integral can be spectrally expanded in the following way. So the first thing is something called a spherical transform of the corresponding test function f, that is we call f tilde. Mu phi is what we call the Langlands parameter of phi. So you may think that for a mass form of mass form of eigenvalue 1/4 per t square on upper half plane, the Langlands parameter are it comma minus it. And then we have an integral over omega of this corresponding automorphic form phi. So by the way, phi runs over non-trivial automorphic forms over which appear in the spectral decomposition. That's what unitary means here. And the main point is that phi is non-trivial. The trivial automorphic form kind of constitutes to the main term in the spectral decomposition. And our goal is to understand this whole spectral expansion without the trivial representation, that this thing is essentially bounded. All right, any question until now? Okay, maybe first let me tell you the main two things that, of course, one would need to understand or to estimate this spectral sum, spectral integral, spectral sum. The first thing is, first we have to understand the inner integral. That's what we call the local L2 norm of an automorphic form. So we have to understand how the L2 norm of phi over omega grows as the Langlands parameter, let's say mu phi, goes to infinity. And the second thing, so this is the first problem, we have to estimate the L2 norm, and we probably expect that this is polynomially bounded in terms of the Langlands parameter of phi. And the second problem is what we call the density of non-tempered automorphic forms. So if you see the spectral expansion, given that this is like bounded optimally, let's say bounded by 1, think about phi being a cusp form, then this thing is trivially bounded by 1 because they're L2 normalized. Then we have to understand how this average over the spherical transform of f grows as this master parameter t goes to infinity. And this is what we call the density of non-temporal automorphic forms. Why is that? Because this f tilde mu phi essentially depends on how much non-tempered phi is. So you can think in classical terms, this f tilde is some sort of Hecke eigenvalue of phi. And if phi is non-tempered, like highly non-tempered, this f tilde mu phi is too large, then this whole sum or whole spectral integral could blow up. But the density of automorphic form, density of non-tempered automorphic form says that the number of non-tempered forms is not too large. So they kind of, the thinness of the non-tempered family compensates the largeness of the spectral transform of F. This is what we call in, or Sarnak calls in Sarnak's, when Sarnak goes this kind of formalize this density thing, he calls density hypothesis, that this kind of spectral integral is not too big. So let me not give you the precise density hypothesis, but this is what we mean by Sarnak's density hypothesis, that the density of the non-tempered automorphic forms is sufficiently small. Okay, maybe let me give you the actual proof for Diophantine exponent, or not actual, but a better sketch than what he just gave, so that we understand what is going on. So I said that we need to choose two things. One is the maximal, one is a compact subgroup inside GL and A. In this case, we choose K to be the standard maximal compact. And the master parameter T is epsilon inverse, which goes to infinity. So remember that epsilon was something very small, or likely to be small. In this case, we choose the test function F to be of the following set. So G is an adelic point. On the Archimedean coordinate, is given by the function is 1 b epsilon g infinity. So b epsilon is the ball of radius epsilon, and 1 b epsilon is the normalized characteristic function of b epsilon, and this infinity means smooth. And the second, on the p parameter, on the pth place, this is given by similar things, but ball of radius p to the power k. So it's a very large ball. In the Archimedean way, it's a very small ball. In the periodic case, it's a very large ball. And when p, any other place other than p and infinity is just something fixed, which is the characteristic function of the maximal compact of the periodic group. So what we want to show, if you remember our previous scheme, we wanted to show that this kf x comma x naught, or x1 comma x naught 1 in the adelic sense. So x is a real point, x1 is a real point. We are extending them by putting 1 in the every finite place. So this quantity is not too small. And to do that, we have to prove that that if k is of this size, to prove the optimal Diophantine exponent, we have to prove that for k of this size, this quantity, this spectral integral, is not essentially bounded, meaning that is bounded by epsilon to the 1 negative eta. So this is exactly what the previous thing was written, but written in a more classical term. So as I said, that this thing is, this f tilde is essentially a Hecke eigenvalue. This is what is given here, that lambda phi p to the power n k, that comes from the Hecke operator in some sense, which is given by the characteristic function of this large ball, and this local L2 norm of phi. And this condition that nu phi, which is the Laplace eigenvalue of phi bounded by epsilon inverse, comes from the spherical transform of the function at the real place. Okay. So as you understand that there are exactly two things we have to consider: how big is this local L2 norm, and then can we apply Sarnak's density hypothesis or something similar to that. So so let me say a few remarks according to for the other question, for the optimal lifting problem. Here the test function is basically dualized. So here we choose, so previously we chose a small ball at the Archimedean place and a large ball at the periodic place. Here we choose the kind of the dual test function. That's what I call is the dual problem. Here the Archimedean place is large. I'm sorry, and the test function on Archimedean place has large support, and the test function on the quadratic place has small support. So KQ is the principal congruent subgroup of level Q, and every other place is a characteristic function of the maximal compact. Okay. So the density hypothesis, the corresponding density hypothesis in the quadratic aspect or Q aspect, is recently proved by Assing and Blomer. So what they proved a similar sorry, I should be, it should be B. A similar sort of problem in the quadratic aspect, meaning when the f is chosen to be the characteristic function of the principal congruent subgroup of KQ. So what is our goal? Our goal is to understand the remaining problem of the in case of in periodic aspect, the remaining problem, and in Archimedean aspect, basically everything is the local L2 norm of the Eisenstein series, both in Laplace eigenvalue aspect or Q aspect, which is Archimedean and non-Archimedean respectively. Okay, let me pause for a moment. Is there any question before I go into the second part of the talk? Let me see how's the time going on. Oh, perfect. Okay.
So in your I think second slide or second or third slide where you stated Sarnak's conjecture, there was some almost every G. Almost every gamma, right?
Right. Yeah.
So does it make sense? Like, so I assume that this almost every means with respect to Lebesgue measure.
This almost every is respect to the counting measure on SLN Z1QZ.
Okay, so like, can someone talk about almost every with respect to some other measure? Like, does it make sense?
I honestly do not know. Also, I'm not a specialist on this subject. Maybe Shai, Ivra, or someone can answer this question. I don't know. Maybe, I don't know.
So I mean, so what does it exactly mean? Like, this is a counting measure, so like this is finite, right?
Yeah.
So it means for all gamma. Like
So
when you say almost every,
as Q goes to infinity, that's the thing.
Oh, okay. Oh,
So
I
as
see.
Q, so the whole point is that there is this Q to the power negative delta. Of course, this would make sense. I mean, this would mean that essentially all but finitely many in case of Q is finite. I mean, Q is fixed, but almost every as Q goes to infinity makes it more interesting.
Okay. So I was confused. Like, I thought it's finite measure. So like, what does it?
Yeah,
What
it is finite, but we have to consider the fact that Q is also going to infinity.
Okay. I see.
So Q is not fixed, and almost every in that sense.
Okay. Thank you.
Any other question? Let's go back to. All right. If not, then let me start the next part, the second part of the talk. Okay, so if you have not paid attention to the first arithmetic part, you can start over again, because this is a completely disjoint from the first part, and this considers a very analytic and representation theoretic problem. Right. Let's say omega is a compact set on the upper half plane, or the modular surface. Nu phi is a measurement of an automorphic form of phi. So nu phi could be size of its Laplace eigenvalue or the level or something. Let me be a little bit vague about that. Let phi be an automorphic form on the modular surface. What we ask is the LP norm of phi restricted to the fixed compact set omega. And let's say phi is unitary. The question is, how does this restricted LP norm grow as the parameters of the family, parameter of the automorphic form goes to infinity? Okay, so an example is it studied a lot, the L infinity problem. So phi is a mass cast form on the modular surface. Nu phi is the size of eigenvalue, the Laplace eigenvalue. Then it's a classical result by Hormander, then a lot of other people. that phi restricted to a fixed compact set, the L infinity norm of that is bounded by the eigenvalue to the power 1/4, essentially. What is the expectation? Expectation is that is essentially bounded or bounded by nu phi to the power epsilon for any epsilon. This is due to Hegel and Wagner and their Randolph-Webb model conjecture. And in case of Hecke mass form, Ivanich and Sarnak has an improvement over the so-called trivial bound. And this is given by nu phi to the power 5 over 24. And there are results of there can be similar results can be obtained by the same proofs due to Ivanich Sarnak or Hormander himself, that the sort average of the L2 norm, L infinity norm is also bounded with the similar strength, meaning this quantity is bounded by t squared to the power 1/4. Okay, there are many other results on higher rank or higher automorphic form, various groups about the local L infinity norm. There is a whole industry about that. Let me not go into that part of the literature, because the main goal of this talk is talk about the L2 bound. Let me go into there. So the problem I talked here, LP bound, so let's say P equals 2, is almost trivial. It's trivial if phi is a cusp-form or a discretely, it's a square integrable representation, coming from a square integrable representation, because then we just bound by 1. But the whole problem is very, very non-trivial if it's not a cusp form or any discrete automorphic form, but rather an Eisenstein series. In this case, we asked that fixing the compact set, how does the local L2 norm on the compact set of the Eisenstein series grow as the parameter t goes to infinity? So we can ask several questions, presumably strictly decreasing level of difficulty. The first one is the L infinity problem. So is the local L infinity norm is essentially bounded. So this comes from following the similar sort of expectation of using the cusp form, that essentially bounded in terms of the Laplace eigenvalue. And here we ask the similar question for Eisenstein series, which is not known by now, even for it's not known. The second question is whether the local L2 norm is essentially bounded. And the third question is whether if we average the parameter t in a very short interval with a high the short interval at a high point, meaning at a large value x and integrate over x to x plus 1, the question is whether this is essentially bounded or bounded by x to the power epsilon at most. Okay, as I said, that we will only focus on last two questions in this talk. Okay, let me talk about a little bit about this truncation, because this will be more useful than when we try to compute the local L2 norm. So for the Eisenstein series on upper half plane, the truncation is a very simple thing to do. What we do is that we choose choose a truncation parameter t, and we define this to be the Eisenstein series, and then truncate off its constant term if it is high in the cusp, the imaginary part of z is large. What is this E0? E0 is the constant term of Eisenstein series given by the imaginary part with half plus it and some what you call some number, let's say. It depends on t and imaginary part of height minus it. And this number is given by the completed Riemann zeta function, or even a ratio of completed Riemann zeta function, C2s divided by C1 plus 2s. Similar sort of truncation can be done for other group. Let me not give you the definition because this is not enlightening for this talk. But the main point is that for every compact set omega, we can choose a t, such that the the restriction on omega has the same valuation as the truncated Eisenstein series. Okay, how do we compute the L2 norm? This is given by the Maas-Selberg formula. So what we do, we compute the L2 norm of truncated Eisenstein series by kind of regularizing the parameter, meaning that we separate out T and make it a generic parameter T prime, and then consider the limit T prime goes to T of the inner product between two generically placed Eisenstein series. And then one can calculate the right-hand side by the so-called Maas-Selberg formula, which is given by 2t, then the logarithmic derivative of r, and then some quantity. The whole point is that this RIT by the functional equation of the Riemann-Zeta function can be seen here, that RIT, if you plug in S equals to IT, this is bounded by 1. That follows from the functional equation. So this thing is bounded by 1, this thing is bounded by t, and this quantity is bounded by log t. The logarithmic derivative of r is bounded by log t. And this follows from the so-called zero-free region of Riemann-Zeta function near the edge of the critical strip, that is near near the vertical axis real part equals to 1. Okay, let us go to the more interesting case, which is the higher rank analog. So let's say G is a reductive group over a number field F. We want to consider the Eisenstein series on the automorphic space of G, which is given by G of Adels mod the G of the rational points, and then we divide by the center of G. An Eisenstein series here can be parameterized in the following sense and following way. So first we consider a Levy subgroup of G. And let's say P is a parabolic subgroup of G, whose Levy is this M. Levy is this Levy subgroup M. And N is the uniformly radical of P. So if you consider GLN, then Levy would be a product over various GLNI, so that this sum of Ni is N. Next, we consider pre-Hilbert space A to P of automorphic forms on GA mod MF invariant by NF. So I'm sorry, invariant by MF and NA. The adelic points of the uniform radical, which are square integrable on M, on the automorphic space of M, that is MA mod MF. This is a pre-Hilbert space, and then the group acts on this space, which is isomorphic to this induced space of the discrete series of M, induced from P to G. And then finally, we have the complexified R vector space of the F rational characters M, which the generic element we denote by lambda. This is, and the space is we call AM mod AG, or complexified version is AMC mod AJC. So in practice, you might just consider the lambda is just AM mod AG dimensional tuple. All right. How do we define Eisenstein series? Is defined by the following. Is defined in the following way. So we consider the an element in the induced space phi. Then we twist by the determinant to the power lambda, and then we average this element by the points GF mod PF. As long as lambda is sufficiently dominant, the average would converge, and then we construct an Eisenstein series by meromorphically continuing in lambda. In particular, unitary Eisenstein series has purely imaginary lambda. So, for example, if G is PGL2, M is the obvious Levy, non-trivial Levy, and phi lives in this induced space, then I phi lambda is given by is essentially the usual classical Eisenstein series. Okay, so we ask the similar question as before. So let's say phi is a unit, and I phi lambda is an Eisenstein series, which is spherical at infinity and invariant by some open compact subgroup of the finite adels. Then there are two questions you can ask. Whether the local L2 norm, again, omega is a fixed compact set, whether the local L2 norm is essentially bounded or at most an epsilon power by the Laplace eigenvalue, the size of lambda, and the level, all the parameters. And an easier question would be if we average the squared local L2 norm, average over a very short interval only over lambda, whether that is essentially bounded. Okay, so our goal is to understand the second problem. So how would we start to understand this problem? So the very basic way, if we just follow what we did for SL2 case, we use the Maas-Selberg relation, or we would try to use the Maas-Selberg relation. So the first problem is, excuse me. So the first problem is how to compute the Maas-Selberg. So Langlands computed the inner product of two Eisenstein series, but he only did so when phi is not a discrete series, but so phi not for general discrete series phi, but only for cuspidal phi. And this is given by some sort of limit as before, lambda prime going to lambda and some average over various parabolics, various Wall elements, and of this quantity. So let us understand this quantity. This m lambda prime is certain intertwining operator in lambda and lambda prime, and depends on lambda and lambda prime meromorphically. Then e to the power st lambda prime is a complex number. Okay, st is a linear polynomial in lambda and lambda prime, and then you divide by certain polynomial in lambda and lambda prime, denoted by theta. Now we see that if we consider trying to understand the limit lambda prime goes to lambda, there could be severe problem, at least coming from the zeros of the polynomial in the denominator when lambda prime equals to lambda, or the poles of these intertwining operators. So remember that intertwining operators are not necessarily holomorphic. So these are one of the major difficulties in higher rank. So even for when the forms are cuspidal, this is quite complicated, and this limiting procedure needs to so in general, each of the summands in this whole average will have poles at lambda prime equals to lambda, but we expect if we sum over various Wall elements and various parabolics, the pole will cancel each other. And this matching up terms for various summands where the pole cancel is a very difficult combinatorial problem, and this is already understood, kind of faced in Arthur's stress. Is there in Arthur's stress formula. So this is the problem number one, and this is even for cuspidal phi. The second problem is we do not just need it's not enough to have the bounds for cuspidal phi, but we have to also understand the same bounds for phi being discrete, or even for coming from the residual spectrum. For that, we have another layer of difficulty coming from the fact that we do not understand the residual spectrum for general reductive group. So there is a formula by Arthur, who computed the inner product of two general Eisenstein series, meaning which are also induced from general discrete series, not necessarily cuspidal. But that formula is only approximate, and then approximation error is not explicit or not useful for our purpose. So that is the second layer of difficulty. The third one is the following. Even when we know the description of the residual spectrum, for instance, the group like GLN, where it is known by the work of Moglin and Wells-Bourget, the limit procedure requires understanding the various higher derivatives. So you understand that when we consider the limit, the summands will have poles, and we probably will group together various terms. And when we compute the limit, there will be derivatives by L'Hopital's. But there is no guarantee that derivatives would be, or a priori, the derivatives would be very high. because we do not know what the order of the poles or how many poles are there, etc. The problem is that we do not know good estimates for those higher derivatives of the intertwining operators. We only know good estimates for the first derivative of the intertwining operators. And those are essentially given by, as you saw in the Riemann-Zeta function case, they're given by the standard zero-free region of the various Rankine-Selberg function. And what we need for a priori higher derivatives is some stronger result than already unknown standard zero-free region. So there are severe major difficulties when we even understand, even for GL3 or at GL4, let's say. So what we know so far is Stephen Miller in his thesis in 2000, he proved the average bound for GL3 using Selberg relation. And if you see his paper, he computed this limit very carefully, combining various terms and canceling the poles. It's a very delicate problem. And this is the highest rank where we know satisfactory answer for every Eisenstein series. And there are some sparse results for higher rank group. For instance, there is a result by Liang Chang in 2019 who proved so 1 by 1, I mean 1 and 2s are this 1 and 2. So this is 1 and this is the 2. So Liang Chang proved essentially the best possible bound for maximal parabolic degenerate Eisenstein series for GLM, which is by degenerate we mean that it's induced from the trivial representation of the underlying Levy. Okay, any question until now? Okay, let me give our result, but before that I have to talk about some terminology. I'm not going to give explicit definitions of any of them, but just try to give some sense what the objects are. So for instance, the first one is the cuspidal data. So what is cuspidal data? Is a GF equivalence class of the Levy and a cuspidal representation of that Levy. An intertwining operator, I already talked about intertwining operator, but in any case, an intertwining operator is a map between the pre-Hilbert space attached to P, or the pi part of that, to a Hilbert space attached to Q. When P and Q are adjacent parabolics, meaning they differ by only one wall element, then there is a standard of writing the intertwining operator in terms only one parameter, S, and it can be factorized at RS, NS, where RS, what we call in representation theory, is a global normalizing constant. There is a certain way of certain way to normalize these intertwining operators. So RS is the normalizing constant. It's given by various Rankine-Selberg L functions. We call a group has TWN plus property if the logarithmic derivative of this normalizing factor, and we consider the moment of that in an interval R to R plus 1 in T. This grows at most log of 1 plus R plus nu pi. So this TWN plus property is coined by Finis, Lapid, and Muller in one of their papers. This is called twisted winding number, or the stronger version of that. Similarly, they have also defined a similar property for the normalized intertwining operator, which is NS. This is a local property because this normalized intertwining operator breaks into local places. So local normalizing intertwining operator should have the property that if it has the property that the first moment of the operator norm, first moment of the logarithmic derivative operator norm is bounded by log of the parameter at the corresponding local place, pi v. Then we call that the G has the BD property. Again, this is defined by Finis, Lapid, and Muller. The interesting thing is that these two properties are satisfied by a large class of groups. For instance, quasi-Placed reductive groups satisfies TWN plus, and at every odd prime they satisfy BD. And these are the results by Finis and Lapid.
The word classical. You missed the word classical.
Oh, right. Sorry. Yeah, you're right. Quasi-plate is classical reductive. Yeah, sorry. Thanks. These are the results by Finis and Lapis, 2017 and 2019. Okay. Let me tell our result. This is quite long. Let me go a little bit slow. So let's say G satisfies these two properties, TWN plus and BD. Let's say K infinity is the, let's say, standard maximal compact of G, the real points, and K is the open compact on the finite ideals. Chi is a cuspidal datum, let's say AM and pi, given by AM and pi, and lambda is a generic point on the imaginary dual of A mod AG. Then we have the following bound. So the first thing is this quantity is just the L2 norm or the local L2 norm. We averaged over lambda prime in a short interval around lambda. Then we averaged it again by three things. The first thing is we averaged over standard parabolics. So this sum P denotes the sum over standard parabolics. Then we sum over discrete series representation coming from the Levy subgroup of the parabolic MP. So pi to m denotes the space of quadrantical or discrete series automorphic representation. And then we sum over phi. So this B chi pi is as an orthonormal basis of A to P chi pi. So A to P chi pi is the A to P is the Hilbert space that we talked before, and chi pi is the chi pi isotypic part of the A to P Hilbert space. And phi runs over an orthonormal basis, and this K infinity K means that phi is fixed by K infinity times K. So we have a long average, very long average over local L2 norm. And what we prove is that this is bounded by what we expect times the number of things that we average over, meaning, or the measure of the whole things that we average over. So this is a sum over P, the same sum, and the dimension of this K fixed space, or K infinity time K fixed space, and the volume of this integral, which is just one. So this is a very tight result, meaning that on an average, on a very long average, the local L2 norm indeed satisfies what we expected. Okay. Any question about this theorem? Okay, if not, let me maybe, if G is GLN, then it will be maybe easier to understand. So let me say it in a kind of classical way that G is GLN, phi is a, say, L2 normalized Heike-Mass form on the space of automorphy from A to P. Then just the local L2 norm only on average over lambda, we have the optimal bound, the sub bound. And the proof is kind of follows from the previous one. So it's a previous theorem, and then what we understand is how to bound these using the classification theorem of classification of discrete series by Moblin and Wasbridge. Okay. So I have like, how much time I have? Like 2 minutes, maybe?
Yes.
Okay. Let me go very fast over this. How we prove this is that we first understand this whole average by what Arthur calls the spectral side of the trace formula, or pre-trace formula maybe, is given by this J chi TF, which is again an average, but over this generically placed inner product Eisenstein series. This RF is the regular representation. That we do by using Pelley-Wiener theory, carefully choosing the test function f on the geometric side, and understanding its spherical transform, which kind of comes here in some sense. And we choose f so that this f in some sense localizes over in a one radius ball around lambda. Okay. The main ingredient that goes into the proof is the GM family of Arthur, is some sense the sophisticated name for the grouping all the terms in the math Hilbert and computing the limit. Then Arthur method gives us is a long sum of, is a long average over various things like the parabolic, some discrete representation, some levies, some Wall limits, and then the integral of a trace of essentially an intertwining operator MLT that depends on L and the Levy and the truncation parameter in some way, and then this projection operator RF lambda on the space A2 pi chi. So what is MLT? MLT is a certain linear combination of various intertwining operators, and the very importantly, they're only first derivatives, not higher derivatives. And then what you do is basically, I'm just giving the big steps here. We use Finis-Lapid's combinatorial lemma to understand this MLT, how they decompose into kind of easier to understand intertwining operators and then derivatives. That's the main point of the combinatorial lemma. Then we apply the Pelli-Wiener theory to bound this lambda integral, or to truncate the lambda integral. And then we finally use these two properties TWN plus and BD, which were supposed to control the growth of the intertwining operator at their derivatives. And that goes into the proof of when you understand this trace and then various sum occurs here. And that basically the total proof, or the major steps of the total proof. All of these parts are very technical. I don't have much time to discuss them, but yeah, these are the big steps. Okay, let me complete here. Thank you for listening. And these are the two papers which came to arXiv very recently. Yeah, thank you.
Okay, thank you very much. Questions, please. Are there any questions?
So what remains is, I mean, if you want to go along the lines of what you described, is to understand the discrete spectrum with a given Caspial data. Is that the issue?
That's definitely one of the issues here that goes into understanding the bounds of that. I mean, this could a priori could grow. For instance, for G2, this could grow faster so that this logarithmic bound is basically destroyed. So you might have some polynomial bound instead of a polylogarithmic bound.
What is the parameter which you vary?
So here, the spectral parameters, let's say the spectrum, the Lagrange parameter pi is going to infinity. So the chi is going to infinity. So the question is, what is the size of this quantity in terms of chi, for instance?
And you're saying that for G2, it will not, you know that it's going to grow?
I don't think we know, but it's likely to be that it's large. If I understand, there's a paper by Kim who proves that the size of this, how to say, so the number of pi that makes it non-zero, this A2, the pi isotopic part, is that number of that grows, that should grow in terms of the chi, or that likely grows in terms of chi, meaning we do not have a good bound. I should say maybe it grows polynomially instead of logarithmically.
Okay, I'll be happy to understand this, but at the moment.
Yeah, and another problem which also there is that the dimension of the K fixed space. I mean, a priori, this could be very, very large. Let's say K is a principal congruent subgroup, even for GLN. Then this quantity is quite high, even q to the power some exponent. It's a polynomial in q, whereas we are expecting something logarithmic. So this is another serious issue here as well. But in all, like for the application part, we do not need to understand, or we do not need the like point-wise bound, but we only have to understand in an average sense. That kind of saves us.
Okay, great. Very nice talk.
And thank you.
Nice result.
Thanks. Dima, you are muted.
I'm not sure when we are meeting next time, but I will send an announcement. Probably somewhere in December. Thanks everyone for coming. Thanks.